Alright everyone, I am Shaurya and this is the solution video for problem 3, Trashy division of TCP Open Contest 1. I hope you enjoyed the contest as well as the problems. So let's dive into it. The problem is Trashy divisions. The problem is Trashy division. Deep within the mythical raccoon realm, where mischief and mystery thrives, two daring raccoons, Drunkenstein and Rory, embark on their nighty adventure. Tonight, Rory has stumbled upon a glorious trash can, filled with exactly n pieces of trash, a true feast by raccoon standards. However, the raccoon cannot simply divide the trash any way they please. In their world, there exists a sacred rule. All divisions must be decided based on XOR maximization. Okay, all divisions must optimize the XOR. This means that when Drunkenstein and Rory splits the trash into two portions, they must ensure that the XOR difference between their haul is as large as possible. Additionally, the law of the raccoon realm dictate that each raccoon must receive at least one piece of the trash. No raccoon shall go empty-handed. Within their sharp minds and even sharper claws, they ponder over how to divide the trash while obeying their realm peculiar laws. Given n, can you determine the optimal way to distribute the trash between Drunkenstein and Rory so that their Zor joy is maximized? Okay, so let's discuss the input. Input will be a single, sorry, input will be a single integer n, right? And the constraints of n is 1e 9. So we can clearly see a big O of n solution will not work, right? So we have to think something mathematically, and obviously it's a question based on bit manipulation. So we have to think in terms of bits. Output format, we have to output two integers that indicates the division, right? Let's say a comma b. So they found a n that is 10, and how they divided it? They divided it as 2 and 8, right? So 2 can be represented, 8 can be represented as 1 0 0 0, and 2 can be represented as 0 0 1 0. The bitwise XOR of it will be 1 0 1 0. The sum is also coming out to be 10, and the XOR is also coming out to be 10. So Drunkenstein must divide 10 pieces of trash such that the XOR difference is maximized. One optimal way is 8 and 2. So 8 plus 2 is 10, satisfying the sum condition. 8 XOR 2 is also 10, which is maximum possible XOR of n. So we can divide n as 1 and 9, 2 and 8, 3 and 7, 4 and 6, 5 and 5. So in this case the XOR will be 0, right? In this case the XOR will be 4. I will let's see. 4 is 1 0 0, 6 is 1 1 0. The XOR will be 1 0 0. So in this case the XOR will be 2. In this case the XOR will be 8. In this case the XOR is coming out to be 10. In this case 7 is 1 1 1 and 3 is 1 1. The XOR will be nothing but 4. So you can see the maximum possible XOR is coming out to be 10. Hence they divided it in 2 and 8. Right, the second input is this and the output for that is this. So let's see how we can solve the problem. So we are given a number n. Okay, we are given a number n. N can be represented as some set of bits, right? If n is 1e9, so it can be represented in 32-bit integer, 32-bit integer, right? So let's say this bit was 1 0 0 1 0 1 0 0 0 0. Okay, so what we should do, we can take the most significant bit. See, in the output you have to see one thing, that the maximum possible XOR, the maximum possible XOR of two numbers less than equals to n will be nothing but n itself, right? So the maximum possible XOR of two numbers less than equals to n will be nothing but n itself. Okay, so how I'm coming to this conclusion? Because let's say n was 15. Okay, 1 1 1 1. Now if we will take any other number, like let's say one number was 15 itself and the other number was 0, so the XOR will come out to be 15. Okay, so the maximum possible XOR could be nothing but 15 itself. So how we can achieve that? We have to divide the number into 2 bits such that after applying the XOR operation we can get the same bit pattern again, right? So if n was, let's say 1 0, we have a contiguous zeros here, then 1 0 0 1 1 0 1. Okay, so what we can do, we can set a as the most significant bit here. Okay, and b as the rest of the bits here. In this way, after we perform a XOR b or a XOR b, whichever symbol you prefer, in this way, after we'll perform a XOR b, the answer will be again n itself. So here a is equals to nothing but 0 0 1 0 0 0 0 0 0, and b will be nothing but 0 0 0 0 0 1 1 0 1. After we perform the XOR operation, the answer will be 0 0 0 0 0 0 0 0 1 0 0 1 0 0 1 1 0 1. I hope you guys know what XOR means. It is exclusive or we can also say it is an odd counter. Okay, so 1 XOR 1 is 0, 0 XOR 0 is 0, 1 XOR 0 is 1, and 0 XOR 1 is 1. These are the operations of XOR. Okay, so we have found a solution that a will be nothing but the most significant bit and b will be nothing but the rest of it. But there is a twist in this solution. What if say n was 8? Okay, n is 8, that means 0 0 some number of zeros, then 1 followed by 3 zeros. Now what we are supposed to do, if we follow the same principle, we will say a is equals to the most significant bit, that is nothing but 8 itself. So a is equals to contiguous zeros, then 1, then 0 0 0, and b is the remaining one, that is n minus a, that is 8 minus 8, that is 0 0 0 0 0. But as you can see in the problem, it was given each raccoon must receive at least one piece, no raccoon shall go empty handed. So we cannot take b as 0. This was the only point in the problem, right? So this was the edge case we have to handle. So in this case, how we can maximize it? Let's see. If the problem was 8, what could be the possible solutions? 1 comma 7, 2 comma 2 comma 6, 3 comma 5, 4 comma 4. The XOR of 1 and 7 is 1 1 1 0 0 1. The XOR is coming out to be 1 1 0, that is 6. 2 comma 6, 2 is 0 1 0, 6 is 1 1 0. The XOR is coming out to be 1 0 0, that is 4. 3 and 5, 3 is 0 1 1, 5 is 1 0 1. The XOR is coming out to be 1 1 0, again 6. And 4 XOR 4 is 0, right? So in this you can see the maximum is coming in this case and in this case. Okay, so we can prove that if we have to select two numbers such that one number cannot be 0, right? If we have to select two numbers such that one number cannot be 0, it has to be greater than equals to 1, greater than equals to 1. the number b has to be greater than equals to 1. So in this case, what we can do, we can take b as 1 only, and then what will happen, the numbers will be remain as it is, only the last bit will be changed. Okay, so in this case the solution will be nothing but take a as n minus 1. So set all the bits of a. So in this case 8 was there, so 8 minus 1 is equal to 7. 8 minus, in this case 8 minus 1 equals to 7, that is 1 1 1, and b will be nothing but 1 0 0 1. So the maximum possible XOR will be 1 1 0. Okay, so the overall solution is divided into two steps. If n is a power of 2, then what we will do, we will take a as 1 and b as n minus 1. Okay, the sum is coming out to be n. Very good. And if n is not a power of 2, it is some other number, then what we can simply do, we will take a as 1 left shifted times the MSB, most significant set bit, MSSB, most significant set bit, and b as n minus a. So again the sum will be nothing but n, and the XOR will also come out to be n, and in this case the XOR will be less than equals to n. Okay, and you might think, but you told that XOR will be always n. Yeah, XOR will be always n, but let's if for example the 8 one, right, 1 0 0 0, we can take a as 1 0 0 0 and b as 0 0 0 0. So a and b both are less than equals to 8, they sum to 8, and the XOR is also 8. So in this case, this statement that the maximum possible XOR of two numbers less than equals to n such that their sum is also n is n itself holds true. But in the problem statement was given that we cannot give a number as 0. So we have to take this way. So let's dive into the coding part. So what I've done here is I've taken the input as n. Now what I'm doing is I'm counting the number of set bits using this built-in pop count LL. Okay. So what it does, it basically gives you, it's an STL library. It's an STL provided by C++. With this you can count the number of set bits. So for example, in case of 10, 1 0 0 1 1 0 0, sorry, 1 0 1 0. In case of 10, the count set bits will be 2. In case of this, the count set bit will be something greater than equals to 1. But in this case of 8, the count set bits will be nothing but 1, right? So if the count set bit is 1, then our first case is here, that is we will print 1 and n minus 1, that is 1 and 7. Okay, but if it was not the case, then what we will do, we will take the most significant set bit. How we can get it? We can get it using log base 2 of the number n. Okay, so here I am getting the most significant set bit, MSSB. Then what is our a? A is nothing but 1 left shifted MSSB. Okay, 1 left shifted MSSB is nothing but, let's say in this case the most significant set bit is nothing but 23. So we will shift 1 23 times to the left. 1 shifted 23 times. That is nothing but 2 raised to the power 23. Okay. And then b will be nothing but n minus a to complete the condition that a plus b is equals to n. And then we can simply print the a and b. So in this case, it is always guaranteed that a and b are always maximized. So thank you if you learned something new. And if you have any doubt, feel free to comment it in the comment section. Thank you.